I'm Chengzhi Mao, and today I'm going to present our work, Generative Interventions for Causal Learning. We often think object recognition works very well today. Here's an image of a shoe. Surprisingly, even the state-of-the-art classifier predicts a shovel. Why is that? Let's look at the attention map. The model is looking at the context instead of the object. The same error happens for other objects. Here's a misclassified broom and a misclassified tray. One reason the object recognition system fails is because of the dataset bias. They struggle to recognize objects that are outside of the training distribution. This has been widely reported in many studies. But let's take a step back and analyze why dataset is biased and why deep models fail to generalize. In this paper, we take a causal perspective. Every image is generated through the causal mechanism, which we formalize as a structural causal model. In our model, we can observe the joint distribution of image and label, which are shown in gray nodes. They are unobserved exogenous variables. The latent environment variable is a confounder, which calls both the label and node BG. The BG variable represents the nuisances like the background, viewpoints, and so on. The FG variable produces the core features for the image category. Deep learning models learn correlation, which take the sphere's environment correlation into account. When environment changed, the correlation no longer holds and the model cannot generalize. To be robust, we need to predict label from image even if the environment has been changed. Thus, we want the classifier to ignore the confounding bias and predict only based on the causal effect. What can we do about it? Identifying the causal effect is challenging, especially in natural images. Ideally, we would do intervention on the images to estimate the causal effect, but images are often passively collected, not allowing intervention, such as moving the camera. There are other techniques in causal inference we can use, but they require making assumptions about the data, which are often overly optimistic in natural images. In this paper, we'll construct interventions using generative adversarial models. Specifically, we steer the GAN to construct the interventions. By going along the PCA direction in GAN's latent space, we can intervene on the nuisance factors, such as the rotation, scale, and the background. Those interventions are often equivariant across categories. This enables us to simulate interventions that is not spuriously correlated with the label. We can also apply the interventions from GAN to natural images via style transfer. Here are the original images and the intervention to apply. And here are the transferred results. Interventions to apply, transferred result. We train our model on the interventional dataset so that we can learn the causal effect. We validate the approach on ObjectNet. Our method improves generalization significantly by up to 9%. Moreover, we visualize the regions that the model used to make prediction. We highlight the attention with red box. Our model makes the right prediction for the right reason. We also generalize better and unthin common corruptions. We test our model on the ImageNet-C dataset, where our approach improves by over 8%. Moreover, we compare our interventional approach with methods that just sampling from GAN. We can see the stronger our intervention, the better generalization we have. This shows that intervening on the GAN is more important than just sampling from it. In summary, we introduce a framework to learn deep classifiers that are more consistent with the underlying causal structures. We demonstrate improved generalization on other distribution datasets. Please see our paper for more details, and thank you for listening.